In this video, we're going to take a look at finding the area under a curve. We're going to start with a warm-up. If you're in my class, you may want to skip on to the lesson. And if you are in my class and you're watching this video, I would encourage you to stop the video, do the warm-up, and then resume the video to see how you do. In this warm-up, we're evaluating indefinite integrals. We're finding the antiderivative of some functions, and in the first function, we're finding the antiderivative of 4x squared, so we're going to reverse the power rule. We'll get 4x cubed divided by the new power over 3. If we find the antiderivative of 1 over x, you might be tempted to think of that as x to the negative 1 and try to apply the power rule, but you'll get x to the 0 divided by 0, and we know that division by 0 is undefined. So you have to ask yourself the question, what function has a derivative of 1 over x? And from our experience, we know that that would be ln of the absolute value of x. And then we talked about in class that there is a plus c, a constant of integration, because what happens is when we're finding an indefinite integral, we either get a general solution or a particular solution. And this one is a general solution because of the plus c. It generates a family of functions, and all of those functions share the same derivative. That's what makes them a family. But the derivatives differ by a constant, and in this case, we were not given enough information to evaluate that constant. In letter B, we ask ourselves the question, who has or what function has a derivative of sine x? And so if we find the antiderivative of sine x, we get negative cosine x plus c. And if you are not sure about your answer, take the derivative. The derivative of cosine is negative sine x, and so we need a negative to offset and make that positive. Again, the c is the constant of integration. This again is a general solution, and it generates a family of functions that share the same derivative that all differ by a constant. And then finally, in letter C, the antiderivative of 2e to the x, that's our favorite function because the antiderivative of e to the x is e to the x. The antiderivative of 5 is 5x, and there's our constant of integration. However, in this particular problem, they give us an xy coordinate, so when x is 0, y is 3, so I have 3 equal to 2e to the 0 plus 5 times 0 plus c. So that gives me 3 equal to 2 plus c. So c is equal to 1. So the particular solution in this case is 2e to the x plus 5x plus 1, and that is a particular solution. It is one member out of the family of functions that share the same derivatives. So those were indefinite integrals. Today in this video, we're going to take a look at definite integrals. And there are two types of integrals. There are indefinite, which is what we were just taking a look at. And an indefinite integral would look something like, find the antiderivative of a function, where f of x in this case is the derivative of some function. And when we find the antiderivative, we generate the original function plus c. It generates a family of functions, as we said before, that share the same derivative. Now, an indefinite integral, it looks very similar. You'll notice one small difference. We still start out with a function who is someone's derivative, except we have a lower bound, a, which holds the place of a number, and b, which also holds the place of a number. So in this particular case, instead of simply just generating a family of functions, we're going to generate a number, a value. Now, how we evaluate or how we get that value, there are a number of ways to do that, and we're going to discuss what the geometric meaning of the definite integral represents in this particular video. So in this lesson, we're going to focus on evaluating definite integrals, and we're going to use or talk about the geometric meaning of the indefinite integral. And as we go through the course, we'll continue to refine this more and more and more, and we'll find some analytic and algebraic ways to evaluate the definite integral. Today we're going to make a connection to geometry. Now, in the problem that we're going to take a look at, we're going to review things that we already know. From our past, we know that if you find the derivative of the position function, and that's what S of t is representing, that we will get velocity. And we know if we take the derivative again of velocity, that we will get acceleration. We've been there, we've done that in this course already. Well, then it stands to reason, if you understand the process of anti-differentiation, that if you find the antiderivative of velocity, then you would go back to a position function. And that's going to help us out in the problem that we're going to take a look at. And if you find the antiderivative of acceleration, then that would take you back to a velocity function. So keep that in mind, particularly in the problem we're going to look at. We're going to consider velocity. Now take a look at that one more time. If you go backwards or find the antiderivative of velocity, you should come up with position or change in position. So let's take a look at our problem. This is in your packet. The big idea, and I'm kind of showing my hand here, the big idea, the definite integral represents net area. Now I want you to pay attention to the word net area. It may not be as big a deal today, but it will eventually be a very important idea. The definite integral represents net area under a curve. So what we're saying, or what I'm saying, is that if you evaluate the definite integral from a to b of f of x dx, it will give you the net area bound by f of x, so the curve is going to be a boundary, the x-axis, and x equal to a, x equal to b. So the curve, the x-axis, and those two, I guess think of it as vertical lines, they enclose a region of area. So there is that connection that we remember how I talked about how we're going to look at the geometric meaning. There's your geometry, because remember in geometry is a course where you did a lot of finding area. So when we evaluate the definite integral here, when we do this problem, we're going to be accumulating the net area. Okay? At this point, you don't need to worry too much about the net area, but as we go on, it'll become more and more important. In this problem, as you drive on the highway, you accelerate to 100 feet per second to pass a truck. After you've passed, you slow down to a more moderate 60 feet per second. The diagram shows the graph of your velocity. So the first thing we want to pay attention to is that the graph that's been given is a velocity graph, and I would encourage you to go ahead and, even though it's written as v of t, just make sure your brain understands that this is a velocity graph. So this curve right here shows how fast you are traveling at any point over this interval of time. As a function of the number of seconds t, so they're telling us then that time is measured in seconds and that velocity is measured in feet per second. All right, let's take a look at number one. What does your velocity seem to be between 30 and 50 seconds? So I'm going to mark off, here's 30, whoops, there's 30, and here's 50 seconds. And you'll notice that that velocity seems to be pretty level at about 60 feet per second. So there's my velocity over that interval of time. Next question is a middle school question. How far do you travel? Now again, if you're in my class, I hope that you're reading these questions and trying them ahead of me instead of just copying this down, and so that you have time to process this and you can start and stop the video as you need. Anyway, how far do you travel is a middle school question. Remember, if you want to know how far you travel, distance is equal to rate times time. So in this case, we know that the rate is 60 feet per second. And we know that from 30 to 50 is a change of 20 seconds in time, so we're traveling 1,200 feet. Now another thing I want you to notice there is that the units for velocity are feet per second, and the units for time is seconds. The seconds divide out and leave you with feet. So that's, you do some of that unit work in science, but I want you to see where the units come from and why it's feet and not feet per second. It's change in position, it's how far you travel. But notice, here's that connection that we were talking about. This region basically forms a rectangle. And if you take a look, the width of the rectangle is 20 units, and the height of the rectangle is 60 units. Well, that's what we found. We multiplied 60 by 20, so what we found is the area of this rectangle, and the area of this rectangle was 1,200 feet. So there's that big idea that the area under the curve is the change in position. If I collect all of this area, let's write in blue so you can see a little difference here. If I collect all of this area, it's change in position. So the curve that we were looking at, that's a velocity curve. The area under that, when I was finding the antiderivative, it took me back to a position function, and I was able to see the change in position, which is 1,200 feet. So there's that connection of a definite integral is the area, net area under a curve. So what we just did here is we calculated, or we did a definite integral geometrically. We started at 30 seconds. We stopped at 50 seconds. We collected the area under velocity. And geometrically, we found that area to be 1,200 feet. That's what we just did. That's the definite integral that we evaluated. All right, now we're going to reset the board here in just a second. Now we're going to move on to a different region of the graph, and as I said, I'm going to reset my board to clean it up a little bit. We're going to look at the distance you travel. I'm looking at number 3, the distance you travel between 0 and 20. So let's clear the board here. And so I'm going to mark off, here's 0, here's 20, and they want to know the distance that we travel. Now remember what we just talked about. What we're going to be evaluating here, let me give myself a little more board space. What we're going to be evaluating here is we want to collect the area starting at 0, stopping at 20, under the velocity curve, and we want to know how many feet that we're going to travel. Now remember, we said that that would be the area bound by v of t, the x-axis, x equal to, in this case, 0, and x equal to 20. All right, so let's take a look at what that looks like on the graph. So we already have x equal to 0. We have x equal to 20. Here's the curve. Here's the x-axis. So we're trying to find the volume, not volume, the area of this region right in here. Now what they suggest for us to do, there are a couple of ways that we can do this. They suggest that we count blocks, which kind of makes sense because this is not an exact geometric figure. You can see there that we have a rectangle, and then the upper region looks triangular, but we're going to do what they suggested. We're going to count the blocks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. I'm going to count that one as 26. It's almost a whole block. Let's see. Maybe these two together, here and here, make about 27. This one and this one would be 28. About 20, I'm getting about 28 and a half. So let's do, we counted blocks and I had 28.5 blocks. Now the other thing you have to be careful of is that one block is how much area. So take a look, here's one block, it's 5 by, what's my scale on that? 5 by 10, it looks like 10, 20, 30, 40, 50, 60. So it's 5 by 10, so one block is 50 equals 50 feet. So when I do 28.5, I have to do 28.5 whoops, let's clear that up. 28.5 multiplied by 50, which gives me 1,425. So the area, the approximation, I should say, the approximation of the area, the approximate distance that I traveled from 0 to 20 seconds was 1,425 feet. So again, we calculated another definite integral geometrically, and that's all this video focuses on, is how to calculate that area or evaluate that definite integral geometrically. Let's see, how many feet? We actually already did this problem. I did the whole thing instead of breaking it into small parts. Here's another example graphically. In this problem, this is also in your packet, the graph shows the cross-sectional area y square inches. So they're telling me that the y scale is in inches squared of a football as a function of the distance x inches, so this is inches, from one of its ends. Estimate the definite integral of y with respect to x. So they want us to evaluate the definite integral. I'm going to call this y of x dx. We're in terms of x, and we're going from 0. So the curve, this is the curve, this is y of x. We're going from 0 to 12, and they want us to calculate the area in this region. We're going to start at 0. We're going to stop at 12. Now let's figure out what our units are going to be. We're multiplying length times the width goes this way. So we're going to have inches squared multiplied, let's do the parentheses, multiplied by inches. So my answer is going to be inches cubed. That gives me a clue that what I'm finding is the volume of a football. All right, I'm going to do that by counting blocks, just like I did before. Let me get this stuff out of here. And you stop and count your blocks. I'm going to count kind of fast, so hopefully I'll do a decent job. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 21, 2, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. So notice what I did is I collected all of my entire blocks, and now I'm going to do the pieces of blocks. So I think I missed this one, 38. Let's see. This and this would maybe make 39. This and this is about 40. I'm just getting an estimate here, so this doesn't have to be perfect. 41, 42. Have I missed anything? Maybe 43. A little more than 44. I'm just going to call it 45 just to make it a nice whole number. So I have 45 blocks. Now remember, you have to figure out how much area one block holds. So this is 1 by 5. So one block is equal to 5 inches cubed. So I have 45 times 5, 225 cubic inches of volume in the football. Okay, so again, we are evaluating definite integrals using area under a curve. Now, for your homework, you're going to be doing the same sort of thing. Now, I do want to start you off on this next problem. And this is where that whole idea of net area that we talked about earlier comes into play. We have a graph. F of x represents velocity and x represents time. Find the total distance traveled. Now, you have to look at what's being asked here. We're actually going to do two things, because since this is a velocity graph, and notice this time we have area above the x-axis, going from, how far are we going to go eventually, to 8. So 1, 2, 3, 4, 5, 6, 7, 8. So it stops there. We have area above the x-axis and we have area below the x-axis. Now, when we're dealing with net area, the area that is above the x-axis would be counted as a positive value, and the area that is below the x-axis would be counted as a negative value. That's when we're finding the net area. Now, in this particular case, since this is a velocity graph, net area would represent displacement, where total area would represent total distance traveled. We're going to do both just to get that idea across to you. So I'm going to make two columns here. On the left-hand side, I'm going to work with displacement. Displacement is the net area. And on the right-hand side, I'm going to work with distance. And the distance traveled is total area. There's where that net versus total comes into play. All right, now I'm going to go back over here and I'm going to estimate my areas. So in the first region, that basically, if you take a look at it, looks like a triangle. It looks like a 2 by 1. So I'm going to estimate my area here. 2 times 1 is 2, and half of 2 is 1. So did I do that right? No, I'm sorry. It's a 2 by 2. So that's 2. Let's erase that so you can see what I'm talking about. This is about 2 units base and a 2 units height. 2 times 2 is 4, and half of 4 is 2. So I'm estimating that the area of that region is 2. I haven't put any units to it yet, but it would be 2 feet. And then over here, it looks like I basically have another triangle. And again, we're estimating, so don't be too worried that we're not getting exact values. That'll come later. So this is 2 by 1, 2, 3, 4, 5, 6, 7. So 2 times 7 is 14, and half of that is 7. And then the area in the region below, I'm going to do that by blocks. So that is 1, 2, let's call it 3, just to keep it simple, just to keep whole numbers. So that region, the area there is 3. Notice it's in red, and depending on what I need is how I'm going to count it. So if I find, let's do letter C, if I find the displacement during the first 8 seconds, then what I would be doing is I would be calculating the definite integral from 0 to 8 of f of x dx. So when I write the definite integral straight across, that means net area, the positive area stays positive, the negative area stays negative. So that would be 2, which is positive, minus 3, because that area below is negative, plus 7 above, that's positive. So that gives me a total of 7 plus 2 is 9, 9 minus 3 is 6. So the displacement of my particle is 6. However, the total distance traveled, there are 2 ways to deal with that. One way to write that integral, and again, I'm still working on part C. One way to write that integral would be to collect the area from 0 to 2, which is positive, minus the area from 2 to 6, and we're subtracting because that area is negative, and if we subtract it, it forces it to be positive. And then we're going to add the last region from 6 to 8 because that area is positive. So if we do that, we would have 2 minus negative 3 plus 7, and that would give me a total distance traveled of 12. Now, another way you can write that is to say we're going to collect the area from 0 to 8. We'll put absolute value around the function, which will force all of the area to be positive because it'll flip that negative region up. We'll talk more about this in class. but this is just your first look at that difference between net area versus total area, displacement versus total distance traveled.